So all things being equal, we should be able to finish our discussion on SQL today. From my projection, uh, we've been dealing with SQL for about 5 sessions now, and hopefully we should be rounding off on that today. Okay, so this is where we left up. Yes, sorry for that. I needed to put that interference aside. Yes, so we stopped at this side last section, and we tried to add natural joins to all the different types of join we had earlier done. The inner join, the full outer join, left join, and right join. Then the usefulness of natural joins to all we are trying to do on that is to show additional levels or additional alternatives to extracting data from more than one table without necessarily having an establishment or an existing primary key, foreign key um, combination. And without the primary key and foreign key combination, we could get to use those joins, and essentially now we can use natural joins. So natural joins, unlike the basic joins, does not necessarily have to um, have the primary key and the foreign key combination. So as long as there is at least one corresponding column that is common to both tables, but the proviso is that these common columns must also have similar data type already uh, pre-specified for each of the tables during creation. So say for instance, if two tables have two columns in common, column one may be, I mean, the first common column could be a column name model, and probably it is model ID appearing as primary key in one table and now appearing as foreign key in another table. Yes, that can be used to act as a point of intersection, or even if they are not designated as primary and foreign key in each of the table, they are just named that way, and they are similar column name for the two tables. Yes, that can be the point of intersection, but the data type specified for both of them in each of the table must be similar, because if data types specified for both of them is not similar, even though the name of the column is similar, natural join will still not work. So we have to go back to the use of basic join. Then you have to decide if you are now using an inner join or a full outer join, a left join, or a right join. And it may not necessarily even be the column that you are looking at to be the corresponding common column for both tables. For instance, the model column can be common, and you may want or you may expect natural join to perform the point of intersection at that point if the two tables still contain one more similar column, let's say dates. And now the dates in column, I mean in table A, is written as date. Then the dates in table B is also written as dates. But if the data type of date specified for table A is different from the data type for date specified in table B, then the natural join will still not work because one common column or one corresponding column similar to both table is having a similar name but different data types specified, and that will not work. So if error comes up, I'm sure the error may just point out where the issue is. Then you have to go back from the use of natural join just to use the basic join. All right, today we are winding down our discussion on the subject of SQL at large, and we just want to brush up on a few things we've done before. Of course, we've done some uh, management features in SQLs, which has to do with the different thing SQL has got to do for us, starting from where the problem lies, from the problem encountered with flat file database and what have you. Now, we also did specify or categorize the different statements and query in SQL. We categorize them into a couple of groups. One telling us that these commands are essentially used for uh, creation and bringing to life some set of data on database, while after the data must have now been resident on the database in one table or the other, you can play around the data in that table too, meaning you can manipulate it, change it, adjust it, make it look the way you want it to be, or update it. So set of commands used to bring data sets into being on a database are different from a set of commands used to play around data in a table resident in the database, as it were. So that's what takes us back to what we call data manipulation language. They are just the SQL commands that we use to adjust, edit, update, and make a particular data already available in the database or in a table in the database to conform to what we now want it to be. It's already there. We are just adjusting it, or we are adding to it, or we are removing some item away from it. So all the commands we use to do that are called data manipulation language. So we are manipulating the data. We are not creating it afresh. So if you want to add extra observation or extra records to an existing data set, so we use insert. If you want to delete, we use delete. You can delete a row or an observation or a record, and you can as well delete an entire table. So we don't use delete for an entire table. We use the word drop. A table is being dropped, meaning a table is completely deleted from a database. So if you want to update a particular field or a particular attribute, in this case, column in the table, you can also use update. You just mention the table name, then mention updates and write what you want SQL to take note of for this particular observation going forward as against what was there. And you can use set and also lock a table on that. So aside data manipulation, we equally have data definition. So I'm doing this just for us to be able to see those things that we have done before and see the very common SQL language that we use every now and then. So for data definition, you are now creating the data table or table afresh, and these are set of SQL commands that are common in that use or for that particular use case. Of course, you have to create, you alter, and you can drop, also rename a table as it well. So in doing all of that, we also went ahead afterwards to uh, put into practice a number of commands, starting from the very elementary ones. They will move as far as introducing a conditional statement, not just trying to retrieve data from a table now. We even went as far as retrieving data from more than one table, and also we went as far as specifying a condition for the output or for the return table that we intend to have from SQL. Maybe we should just quickly check that and see how do we brush that up again. Um, yep, where's my SQL environment? Okay, there you go. So I think I almost made that mistake again today. You need to check where you are to be sure of which database you are currently on. So you can just say show database just for you, just an healthy practice, just to know where you are. So you put it in plural, show databases, you just want to see how many databases are there. It lists it out for you. Then you can tell it to use a particular database you have in mind after listing it out just to be sure. I have school underscore demo. I put this back as semicolon just to key in the query. Then I run it this way. Then it lands me on the fact that I am now on a database called school underscore demo. All right, that's fine. On school underscore demo, I can also say, okay, go ahead and show me how many tables are available in there. So I can have a view. I just say show tables, then run it again. It brings out all the tables. So I have bike underscore model is the name of a table. Bike underscore sales is the name of a table. Meals is the name of a table. Shapes, students, and teachers. So having done that, we equally went as far as mentioning that the most common or the most uh, commonly used SQL query is the word select. It is an SQL statement and it is the most commonly used because you can hardly do without it when you want to interact with an existing table. So what are you saying? You are saying select. You can say you can choose to go ahead and list out the columns in the table that you want to see. If the table contains like say 5 to 7 columns and you necessarily don't want to see all the columns, you just have in mind maybe 2 or 3 to see. You can specify the 3, but generally, we just bring out the entire set of columns in that table. And you use this notation to do that. It says select star. That star implies all in SQL. So select all. Then you also go ahead and mention the table from where you want SQL to make selection, and it will return that particular entire table to you straight away. So in this case, having seen that, okay, I have bike underscore models, I have bike underscore sales, maybe I should just go to um another table this time around. I can say select all from a table called shapes. Then I have it this way, highlight, run. So it brings this entire table out for me. So in a table called shapes, I have the first column, which appears to be the primary key column, and that is the ID. And each observation, the meaning of observation in data analytics is row. It also means record, and it is the horizontal representation in the table, which is the rows. So each observation, each row has a unique ID number, and that shows that that ID column is the primary key column that makes one row different from another. If you check some other columns, you will see that some of the entries in those columns are repeated across the rows. Those columns are not primary because they are not unique to a single set of observation. So the one that is unique to a single set of observation is always the ID column. More often than not, they are used as the primary key columns, such that anytime you need to extract data from this table in conjunction with another table, it is this ID column that will help you specify entries coming from this table different from the one coming from another table, and just an addition of another column from the other table that will eventually be pulled out. So having said that, I can say, okay, select all from this table called shapes, and it has pulled out the entire columns in this table for me, including the entire row in the table. I can give a condition and go further to say, okay, what I want you to do is select quite all right from this table, but I don't necessarily want to see all the entries. So I want to give a further condition. So I can come down here and just say, okay, select all from the table, but ensure that you only pull out for me um, entries that falls within this condition. So I need to specify the condition. Now, what is the condition? The condition is that where I can now look at any of the column. Okay, I have shape, I have color, I have dots, X log, which is X location, Y log, which is Y location, and scale. So I can say, pull out for me where dot, which is the name of a column in this table, where dot is greater than 3. So the further condition I have issued here to SQL is that, okay, go into this table, pull out the table. But before you pull out everything, make sure you only pull out or you only return to me outcomes whose dot column or dot value obey or conform with this condition. What is the condition? The condition is that that dot value must be greater than 3. Here, I have entries whose dot value are less than 3 and also greater than 3. So, but now I only want outputs whose dot values are greater than 3 alone. So let's see what SQL is going to do. And this is so fast and easy because if the data we are talking about, the data is relatively just for dummy and practice and just so small. On a good day, you may have a data set having rows numbering up to tens of thousands. So that is where the real beauty of SQL comes alive to you and say, okay, just by just writing normal English, put correctly, and applied correctly as SQL will understand it, then it goes ahead to give you an output or a report that accurately represents what you have specified in question. So I will run this code now, and on running this code, let's see what it brings out. Don't forget we have how many lines here, how many rows from 0 to 15. Yeah, that is 16 rows. All of them, both those whose dot values are lesser than 3, equal to 3, and also greater than 3. But now we are telling SQL, just give us the ones that are greater than 3 alone. So we don't want to see anything 3, and we don't want to see anything less than 3. We want to see from 4, which is greater than 3. So let's see what it pulls out for us. So select from shapes. Yeah, so why did it not run before? All right. I was specifying a column for a condition. I wrote it as dot, which is dot. Whereas if you check very well, the dot is not just dot, it is dots. That was why it gave me an error initially. So I need to correct that and make sure I include s such that that place is now complete. So I remove this semicolon here so that that error will disappear, correct? Then I can come back here, highlight these two guys, then run it back. You can see he's giving it to me now. I have specified that I want entry from that same table that has 16 elements in it, but those entry must have their dot value greater than 3. Can you see? It has gone ahead to give it to me. I do not have anything 3. I must not have because I have said it must be greater than 3. So it will go ahead and look for something above 3 and beyond. So I can see I have dot value from 4, I have 5, then I also have 6. Those are the values it has brought out. So just as this is done, I can equally say, okay, this is just from a single table. Can you also go ahead and pull out entries for me from two tables such that I have um, I have the columns in the particular table. For instance, okay, let's go back to bike underscore model and bike underscore sales table. So I can have this here. So I can first say that, okay, you stay here, select all from bike underscore model, put this here, run it. So let's see bike underscore models table, and that is just this. That is giving me bike underscore models. So second one, I want it to be bike underscore sales, just for ease of running the code. So I have ID column, I have model column, I have color underscore option column, then I equally have cost column. So here I can go ahead and say, okay, those are the different columns in bike underscore model. Can we see the columns available in bike underscore sales? I run the code. Yep. This time around, I have transaction ID column, I have customer ID column, I have model column, I have color, I have sale underscore price column. So these are also all the columns in bike underscore sales. So just like we use join to extract data from two tables initially, we could also go ahead and use a natural join to extract data this time around. Do not forget, when we are using natural join is just that, okay, there may not be any existing foreign key, there may not be any existing primary key. So there is no primary foreign key combination, and there may not also be any existing um, specified uh, primary column in either tables. But if there is a common column, sometimes it is called corresponding columns. If there are corresponding column, meaning the two tables have at least one column name in common. And that appears to be the case in this example because in bike underscore sales, I can see transaction ID, I can see customer ID, I can see model of the bike. And I can also see color of the bike. Then I can also see the selling price, which is the sale price of the bike. Same way, let's quickly check bike model, the model of the bike. What can we see? It has ID, it has model also. So there is already a common column or column that is common to both tables. So even if both of them do not have primary key columns, it does not matter again. SQL can still pull out data from the two tables without mixing up anything. It will align it perfectly based on the entries on each row accurately. And what we can do to get that done is natural join. We can just use natural join. But the only condition before we can go ahead to use natural join is the fact that um, we must ensure that the columns that are common to both tables are not just having similar column names. The data type in them must also be similar. How do you know data type of the different columns in a table? Yep. What query is that? We can use describe. Okay. You can tell us Excel, Excel, Excel. You can tell SQL to describe for us. So describe, mention the table name. You can say bike underscore sales. That's a table name. We want SQL to describe it for us. Description simply means show to us the different data type specifications or the schema, so to speak. Can you show me the schema of this table called bike underscore sales? Don't forget what we call schema. Schema is the structural configuration for each table specified during creation. So it has to do with data type you have put in there, the number of characters that each of the columns should have, and some other unique things you want it to be. And it also includes if you are setting any of the column to be a primary key column and you want to make the primary key to also self generate itself. All of those things are already specified under schema. So let's describe this. So describe this table for us. Let's see this. So describe bike underscore sales, run this. Yes, the description is out now. In the description, it's telling us that the field, don't forget, field means columns. The field or the columns available in this table called bike underscore sales. The columns are called trans ID. Don't forget, I did it for us the other time. This is this table. Does he have trans ID? Yes, column trans ID. Does he have customer ID? Yes, customer ID. It has model, it has color, it has sales price. So let's go back to describing it now. We now want to know what are the data types specified for all of these columns in this table when it was created. SQL can bring that out for you so easily this way. So yes, it's now showing it as field, which I said it also means column and it also means attribute. Those are the words SQL uses. So trans ID, what is the type? Data type is already specified. Can you see it's integer? Was it set to be null? No. Is this trans ID a primary key? Yes, it has written it there. It is a primary key. What are the extra information that is also included in this column when it was being created? It was set to self generate. It was set into auto increment. That is, that ID column can increase by itself and generate new ID for every new entry added to that table. The person adding it does not need to create the ID for that new entry. Automatically, this table will generate a new ID for any new line of record or observation or rows you are adding to the table. In the same way, customer ID column is also an integer. It was set to integer, and um, yes, it was said to be null. Yes, it's not a primary key. That's all. And that's how the rest were also done. So we can also do same for models. Where's models? This way. Sorry. Yep. So the field in model, field ID is also is set to not to be null. It's an integer. It's also primary key. Other one follows suit, just like that. So the rest can see variable character, decimal, which can also be said to be float, and what have you. So these are different ways you can get to see things that have been set as far as specification in SQL is concerned. Now, I now want to join these two tables together. I want SQL to list out all the columns in bike underscore sales and also list out all the columns in bike underscore models. So I can just easily use natural join. Why am I using natural join? I have established the fact that there is a common column. We call it corresponding column to both tables. In this case, that column is model. And I have also checked to see that the data type for model is exactly the same in each of the table. Can you see the data type for model in this particular table, which is bike underscore model, is variable character and it is set to limit of 50. Let's see same thing for sales to be sure that it's also a variable character and it is set to 50. Then that makes it fantastic. Model, data type, variable character, and it's set to 50. So that makes model column our point of intersection for the two tables. So natural join can work now because all conditions have been fulfilled or satisfied. In that case, I can now go ahead to tell SQL to pull out the columns from both tables. So that query is here. Select everything from bike underscore model, then naturally join it to everything on bike underscore sales. So let's see what it brings out. Yes, this is the two tables now. It has merged together all the columns in bike underscore models and all the column in bike underscore sales accurately using model column as the point of intersection without mixing row 2 for row 3 or row 4 for row 5. And that's exactly what has been done here. So these are sort of different play arounds we can have. We're working on one before earlier. Okay, we're working on shapes. Let me bring that one out just momentarily again. Yeah, this is shapes table. And we have said, we have added a condition that it should only give us where the value for dots is greater than 3. I want to change it now. Maybe I can say where no, that is not this one. This one is here. Yes. This is the table I wanted to bring out. So where the value of dot is greater than 3, I can just simply say, okay, I don't want to use dots to establish that condition. I can use any other columns in this table. In this case, I can say where scale instead of dot column. Now I can use scale. I can use anything to establish the condition where scale value is, let's say, um 0.5. Yes, I'm saying it's greater than, where C value is greater than 0.5 now. So let's see how many is going to pull out. Oh, wow. So I have all of these greater than zero point 0.5. So it still gives me 0, 1, 2, 3. Okay, there is no 4 there. 4 is not falling into the category. 5, 6, 7, 8. 9 is not there too. 9 is not falling into the category. 10, 11, 12, 13, 14, 15. Yeah, about 3 rows are sieved out here. Row 4, row 9. Yep. Row 9, 10, 11, 12, 13, 14, 15. So row 4 and row 9. 1, 2, 3, 4, 5, 6, 7, 8. So 4 and 9, just two columns are excluded there because of this extra condition that was specified. So if I had just said, okay, I want you to pull out everything from that table for me, you can see all of them will be complete now. I will now have row 4. Then I also have row 9 that was not there before. Just check very well. There is no row 4 right here in this table, and there is no row ID 9 right here on this table. When I ask SQL to pull out the entire table for me without that condition, it will add everything and I can see. You can see I now have my row 4 because I'm pulling out everything in the table, and I have my row 9 because I'm pulling everything out from the table. I can go ahead just to say, okay, I do not want to use scale to sieve or filter again. I want to filter using a different thing entirely. I can use the color column to filter. So where color cannot be greater or lesser. So you just say color equals to, yes, that is the condition. Just put one color name this way and end the argument. It's showing error, something is wrong. So I have ended the argument for that code twice. So I need to remove one, then the error will disappear. Okay, so I have the two this way. I want you to give me all the entries in this table called shapes, but only give me the ones that have their color value to be green. even though I want you to pull out from the entire table. So if the entire table have their color value to be green, all well and good, give me the entire table. If the entire table only have 70% of its entry in color column to be green, then that's what you should pull out. So go into the entire table first, then now narrow down or drill down to obey this condition I have specified. So by the time I go ahead to do it now, I need to run this PIM. Oh, there's an error. So there's something wrong there. Yes. So what happened is that when you are dealing with what do you call this data type now? That's another very important thing that happened. In talking about a data type, um, yeah, this is what we call string. In using string, string is just a continuous combination of both numbers and letters used together in data or in programming, as it were. So computer sees it as a string. So when you are introducing a string, you need to put it in quotation so that the computer can know that you are dealing with a string. So I have put it in quotation now. Yes, so it should be able to understand what we are talking about and not give me error again. Okay, run this now and give me fantastic. So this is the output. It's now showing to me the entire table for those entries that have their color value only to be green. Why did it not run before? I did not put quotation on the green because it's a float, it's not number. The other ones, they are numbers, they are integers. I don't need to put them in quotation. So those one ran correctly very well. But when you are now dealing with a data type called string, you have to put it in quotation. So I can change the color. What other color is there? I think I saw orange. Yep. So let's see if it's going to give me my orange. This way. Yeah. So it's giving me the table, but narrowing it down to the ones that have their color values to be orange alone. And I can manipulate and manipulate all the more around it like that. So those are the sort of things we've been able to do and play around with Excel. With SQL. Let's see a few things remaining for us to know as we intend to um, is there any question? As we intend to round off our discussion on SQL today. Okay, so I go now to what is it called? Um, yes, back to the curriculum right here. So aside the relational database which we've been dealing with and for which we've been learning SQL to be able to know how we can navigate around um, the database called relational database, which is a perfect substitute for the flat file database because of the restriction that flat file database had, which relational database came to solve. We have also discovered in the advent of the high volume and heavily voluminous volume of data that is being generated now in this age and time, which is the era of Internet 3.0. So Internet 3.0 is now making Internet of Things to be heavily increasing and dynamic because devices being created from technology every now and then, all of them are generating data and all of them are pulling out as many data as possible within milliseconds on daily basis around the clock. And when is being generated as it were, they are not just generated and thrown into the air. They are captured somewhere in a log, which goes into a database at the end of the day. So to keep up with the speed with which the devices technology has now produced uh, is churning out data, there is also now need to see what additional thing can be done to capture this heavy volume of data that is now coming. Don't forget, relational database takes its time to specify structures, specify schemas, specify columns and rows, and the format in which the data are to enter the database as it is. But the rate at which data is being generated this day, it is almost becoming impossible to catch up with that pace. How do I mean? Relational database is essentially about um, the relational database system software. One, it comprises of three things: the relational database system software, one, that's the element one, and that software sits on a server. Server is the second element, and of course, the third thing is now the disk or the drive where the data is being stored. So those are the three distinct components of relational databases. And how that is done is such that the server are in physical location. I mean, installed somewhere, and the software on the server, and they are performing their operation based on the interaction they are having. And of course, as the data is equally very, very robust, relational database is quite robust. So as data is increasing and all that, it's also increasing to accommodate those data that is coming. But the rate at which things are happening now and the type of data that are being produced, uh, number one, they do not conform to the format in which relational database can easily absorb them and get them stored. They need some sense, I mean, some form of processing before they can get to the format that can be adaptable to relational database. But the rate at which data is being produced is expected for data to be captured that way and be stored. That's one issue identify, which relational database has not been able to catch up with. Then, secondly, is the rate at which relational database process the data vis-a-vis the rate at which different data are being produced these days based on the different number of equipment and devices, wristwatch, glasses, computers, all sort of things are generating data, and relational database cannot necessarily catch up with that because all of this has to go through that server. The server works on it and it's now getting stored inside the disk, as it were. That length of time or the time required to get that done is not in consonance with the rate at which the data is being produced, and that will not eventually be efficient or effective. So what is now being discussed is that there is need to have a cloud arrangement such that we can have a distributed processing. So the relational database does not need to just be set of giant computers seated somewhere, and they are the one doing that work for a particular multinational or a particular big firm and all that. It could be a combination of thousands and millions of computers everywhere in the world, and the set of data that is being received at one point is within that moment distributed across all of those computers everywhere for them to process. So there can be a very large data project, and there could be thousands of computers working on processing that project, and each of the computer is set such that each of them is doing the one allotted for it in that big project, and they will pass it through established process where at the other hand everything combines again to give the clearer picture and all that. And if one is redundant at one point in time, another one can pick up where that redundancy occurs and rectify it, then still return the correct response to the main server at the end of the day. And that has shown to be very, very efficient and effective, which could not be achieved with relational database. And that's exactly what we mean by distributed data and NoSQL. So NoSQL simply means non-relational database or no structured query language, meaning that you are not supposed to be confined to, I mean, data is not necessarily confined to the schema designed or specified by a particular database before it can be worked on, processed, and later returned to be stored. So those are the sort of things going on currently, and that is what gave birth to what we call big data. Currently, we are dealing with big data, and the only thing that can process big data efficiently and effectively is distributed data system that are located several places in the world or several data centers all across the world. So a large chunk of data projects can be divided amongst thousands of data processing centers, and they will work on it and they will deal with the different type of data that is there. So unlike relational database, it must be a particular type of data and it must conform with the specified schema for that database before that process can work smoothly. But this case for NoSQL, it doesn't have to do with a particular type of data. Any type of data is welcome because there are processes to take care of each of them and still eventually get them processed and combined at the end of the day to be properly stored in the database. So what are the types of these NoSQL databases that are adding extra layer of better processing of big data? Don't forget, where NoSQL is shining is because of the big data. Excessive large amount of data in unstructured formats turning out in zillions. As I cannot even mention what type of amount is so huge and is happening on per second basis. No thanks to the advent of AI again, working on all sort of data, digesting data, and processing data even almost faster than the speed of light. All right, so what are the types of these NoSQL databases? Number one is key value stores. Number two is document databases. Number three is graph databases. And number four is white column stores. So for the key value stores, as the name indicates, it stores key value. In this case, it is similar to the primary key that I mentioned under relational databases. So it concerns itself primarily to the key value, and it can store as much as possible of this key value. Of course, relational database can also store key values as it were, but the optimization capacity this particular key value store database has is what relational database cannot cope with. And this is just an example in this figure. This what is concerning itself with is key value. Those numbers that are key in that particular column called key is what that database is concerned about. And as long as you can pull out that key number, regardless of the number of other field entries, all of them will be pulled out so easily. So the next one is document databases. So for the document databases, um, this processes documents. So that goes back to what I mentioned earlier, that in this day, in the era of big data, data does not appear in form of text and columns again. It doesn't appear in form of just number and letters again. It's not as a text file. Data appear as a normal file, like Word document, and you have to find a way of scanning through that document and extracting data from it. Then if you want to put it in rows and columns, it's left to you based on what capacity the software has got. So, but for relational database, you cannot send or upload a Word document or even a PDF document to relational database and you expect relational database or SQL to analyze that and put it in form of table. It's not going to work. It is designed to only see rows and columns and only looks for numbers and letters. So something you now put in form of a letter or in form of a book or in form of a page, and you want it to turn into a data, is not wired to do so. So, and we have a lot of such thing in this time and age of big data. Data appears in all sort of forms. So another database that can help to deal with that is what we call document database. This one uses this particular tool called JSON or BSON or XML. scan through the document intelligently and fetches out information from it and can put it on a table if you so want. So, and this is how it works. It can generate an ID for it, give it a name, get some columns out of it, arrange it in order of the document name and all that. So the third one is what we call graph database. So graph database use nodes, and the nodes are connected to each other, just like in form of a community or a network, and it looks more like a graph representation. So all these are things that are not possible to be handled by relational database, because you cannot draw a shape as a node in circular form for relational database. It doesn't have an idea of what you are doing. So, but this is a specified database, graph database. So it could be MongoDB, it could be any of those graph databases that have been designed to be able to handle things like this, and it will handle it effectively without mixing any information. So it can also generate a graph out of it. So the node can, for example, be representing a user in a network or in a social network, and how that particular user is connected to as many friends as possible, just showing different uh, tree connection in a network. Your friend is connected to other friends, and you are also indirectly connected to that other friend. You are level one ahead of one particular person as your up head, to show those direct link and the indirect link, and how everybody is connected in graphical formats. So an example is how this is in this shape here. So the final one is the wide column stores. So this one store information in tables, just similar to relational database, but it is different. The difference between them is that the columns do not represent attributes. Those columns rather represent values. So in relational database, all columns you see, they are fields, and they are representing a different attribute of that data set, different from each other. But the columns in this kind of database are not representing field or attributes. They are actually representing value. And it's a bit complex because both the horizontal and the vertical are giving you different things to look out for, but the data point inside of them can be anything, just as we are seeing here. So those are the different what is it called now? The different database type that we could also explore under NoSQL, which is non structured query language, as a build up or as another additional layer that is building on what relational database has done. So, relational database has got its advantages, but in the light of the tsunami of data and the different format in which we now receive data, relational database does not have capacity to capture or take care of all of those. So that is exactly what gave birth to NoSQL databases, which SQL cannot actually handle. And that is the way we could capture them without losing any data, which are eventually or ultimately essentially needed for some analysis that will inform better insights and better hidden instructions that management could take advantage of to redress operational processes and make some improvements on performance in general. So, on that note, those are the different things we needed to add in our study of SQL, and finally down to what database is being added to relational database, which is the NoSQL databases, because of the reality of big data the world is currently facing. Is there any observation, any comment, question? So, in the absence of no question, we have all the pack. We have the list of the different recordings already done on SQL. By next section, we are moving down straight to um, a visualization tool called Tableau. So we are going to pieces Tableau from scratch again. Just like we have dealt with every other tools we have picked, we have dealt with Excel, we have dealt with SQL, we have dealt with, we just finished our dealing with SQL now. So we are moving down to the use of Tableau as a visualization tool, which is similar to Power BI. So after dealing with Tableau, maybe for some 3 to 4 or 5 sessions, so if we still have a little more time, we can pick up another tool before we run the final curriculum project, or we can do the project while we pick up another one as time progresses, whichever is more suitable as at that time. If there is no other question, then we can draw the curtain at this point. Thank you all for your time, and we'll see you again next session. Bye for now.